Let us take one more interesting example. Look at this. See, here I have taken, of course, both the carbons are in the same environment. But the point is, which one gets shifted towards the carbocation? No problem. In the formation of carbocation, you don't have any issue because you can take any of these as both are in the same environment, right? Let us take this and form a carbocation. Straight away, now the interesting part. Now, what is to be shifted? You got two options, a phenyl group and a para-NSyl group. Now, anyway, you are going towards a positive charge. I mean, towards something which is electrophilic. So, you need to actually shift something which is more nucleophilic. See, out of these two, you know, this one is more nucleophilic. So, let me shift this towards the positive charge. Okay. The more nucleophilic goes to the rescue of the positive charge, goes to the electrophilic end. So that is very important. So this is a bit complex thing. Even here also, I'll be giving you a migratory aptitude, bit complex one. But let me first finish off this. Yes, you get a positive charge. So 1, 2 para NSyl shift. Okay. Now, as usual, remove this. Okay. So this is a final product. Now let me give you the migratory aptitude again. The more nucleophilic migrates first. Now, if suppose we take some nucleophiles into consideration, para-N-acyl with the plus M of the oxygen is more nucleophilic. Then let me take para-toluyl. I mean with methyl group, which of course is plus I and hyperconjugation. Then the basic phenyl with no group at all. Then something which is withdrawing. Okay. So this is how the migratory aptitude can be given. N-acyl, toluyl, regular phenyl, and then chlorophenyl. So from this, we understand that the knowledge of more activating, more deactivating thing is of course needed for this. Now one more. Something of this type. Let me first generate a positive charge on this carbon so that the positive charge is stabilized. Okay. By plus I. See, if we simply generate a positive charge at this carbon, now that will be less stable because this particular group, I mean the cyclobutyl one, has got steric or let me say angle strain. It has got some strain. So let me first develop a positive charge on this carbon. And now let us try to make the ring get relieved from the angle strain. Okay, come on. This is how we can go for ring expansion. Which of course relieves the ring from the strain that it has. Look at what happens. Now the bond is between these two. It will now go and get connected to this carbon. Then this also. The carbon which has got two methyl groups. Now this is where we have our OH group. And no doubt this carbon has lost its bond. So a positive charge. Right? Then this to get the final product. This is, of course, a 5-membered ring. Double bond O to the carbon next to it. we have 2 methyl. This is what we get. Okay. Interesting. Now let us go for semi-pinnacle pinnacalone type of reaction. It's called semi-pinnacle pinnacalone. Interesting. But why? You will have an extra step. Let us take this example to find out why is it called semi-pinnacle pinnacalone. Look at this. Now this is a primary amine, NH2. It's not a regular pinnacle or it's not a vicinal diol, but has to be converted into vicinal. See, this is now treated with nitrous acid. How? By reacting with the sodium nitrite and say HCl, isn't it? Now these two react to form nitrous acid in situ, and the process of course is diazotization, right? Now simply this, which is a primary aliphatic amine, 1 degree aliphatic amine group. On diazotization, as we have already seen, this is going to get converted into a carbocation. Of course, the carbocation will have different possibilities, but here, you know, okay, if suppose you want some more clarity, let me give this way. This will become a diazonium salt. Now then the bond will go towards the positive charge. So that is how a nitrogen is eliminated. N2 is last and we get a carbocation. So a positive charge. Now just go for ring expansion again. Even this 5-membered ring has angle strain. Next. Okay. Then the 5-membered ring. A positive charge on this carbon. Because earlier the bond was between these two. This is still holding its bond, is retaining the bond, but this carbon has lost its bond. So a positive charge. And now it's loss of proton to form this. Now let us take it here. To the carbon adjacent to that, we have a 5-membered ring. So this is semi-pinnacle pinnacalone having an extra step, diazotization, wherein the amino group is first converted into a diazonium salt, and then the loss of nitrogen. Of course, the Cl minus is also lost to form a carbocation. From then, simple. This is semi-pinnacle pinnacalone type reaction. Next, let us go for the formation of hemiacetals or hemiketols and acetals are ketols. Let me tell you what hemiacetals or hemiketols first. A carbonyl compound when treated with one molecule of an alcohol look at this. Now we get O minus and of course this positive charge. Now remove a proton and give the bond to the positive charge. Now see here, this proton is given, or let me say is abstracted by O minus. So we get OH and here it is OR. Now this is what we call hemi. If it is an aldehyde, we call it hemiacetal. I mean, if this is R and this is H, of course, this can be even H also. This is hemiacetal, isn't it? from an aldehyde, or it can even be this. If suppose it is, two alkyl groups, may be different also. This part is very important to call it a hemiacetal. A very important thing which will be very important in finding the reducing sugars and the non-reducing sugars when we go for carbohydrates. Now, this is called hemiketal. With keto. Okay. Now, let me give you the mechanism. First, acid catalyzed. Let me take H3O plus here, acid catalyzed. If we take H3O plus, we get water as the byproduct. And if suppose we take alkyl group here, we get an alcohol. Look at what happens. Abstraction of proton, then this. So a protonated alcohol is what we have taken. Now, this will be along with this, of course, we get alcohol. Now let us take it this way. Acting as a nucleophile. When it attacks the carbonyl carbon, the bond migrates this way. This becomes OH. Then this, of course, with a lone pair and a positive charge. Now, taking another molecule of alcohol, we can abstract this proton and give the bond with a positive charge. That is how we get the final product. That is hemiacetal or hemiketal. OH, here it is OR. Of course, along with that, we get what we have taken in the first step. The protonated alcohol. Okay. Next it is the base catalyzed formation of hemiacetal or hemiketol. Let us take alkoxide a minus, then this is OR. On further reaction with alcohol, proton is abstracted and this will go towards the oxygen. That is how we get a hemiacetal or hemiketol. Along with this, the alkoxide again. Okay, so this is about the formation of hemiacetal or hemiketol via acid catalyzed and base catalyzed mechanism. Now it is the formation of acetal or ketol. A carbonyl compound with alcohol. See, initially we get hemiacetal on further reaction with another molecule of alcohol in the presence of acid. So this is very important here. See, in the first step here, you can either go with an acid or a base. I mean, the formation of hemiacetal or hemiketol is either acid catalyzed or base catalyzed, but the formation of acetal or ketol is always acid catalyzed. Okay, so this is very important. This is acetal or ketol. Okay, now the mechanism. As I said, only acid catalyzed. Abstraction of the proton. You get along with that the alcohol. First step is of course the same as what we have seen in the formation of hemiacetal or hemiketone. As and when this attacks, this will go towards the positive charge. Then we get OH and this. As usual, this proton is abstracted by alcohol. Take out the proton, give this bond. Okay, that is how we get a hemiacetal. Okay, now when this hemiacetal is further treated with another molecule of protonated alcohol, of course, that gives rise to another molecule of alcohol in the next step. Look at what happens. Repetition of the steps. Okay. Now from this, we can just remove a water molecule to form a carbocation. Okay. Now this is again attacked by the alcohol what we got here. Take it this way. Now we get this. Okay. Using an alcohol again, remove this proton, with the bond to positive charge. That is how we get the final acetal or ketal. Along with this, of course, the protonated alcohol. So this is a mechanism of the formation of acetal or ketol.